All right, good morning everyone, and welcome back to Algorithms and Data Structures for a tutorial session. So once again, let's see how this goes using Twitch for this purpose. Let's quickly check again. Can you hear me? Can you see me? Does it all seem to be working? Excellent. Good. Okay. Then let's see if we can get this started. So before we begin, one announcement from my side. I got some time yesterday evening to do some grading. So the written exam is now graded for about 50%, as well as the implementation exam. So it looks like I'll be able to make the self-imposed deadline of Friday. Of course, I still hope to finish it a little bit earlier, but Friday should definitely still be possible. What else did I want to say about that? Yes, so one, let's say, spoiler warning already for the announcement that will accompany the results. Some of you already noticed during the exam that there was a small mistake in the second exercise in the spec tests. No matter what you did, you would always, well, that's not very true, but even if you didn't type any code, you would pass all the spec tests. That was a mistake on our part, and I'm looking into how to compensate for this. So there will probably be, depending on how the exercise is made, but I've seen already some people who likely thought, well, I passed all the tests, I must be done, whereas they were still missing a use case. So there will probably be a small compensation for that. What else? I think that's it for me. If you have any questions, feel free to already post them while I go over what we're going to do today. So, as I announced yesterday, because I have a little bit less time than I'd hoped to prepare videos for you, today is going to be a bit of a mix between a tutorial and a lecture. So for the first half, we will do a tutorial about maps, our topic from yesterday, and the second half will be about graphs, and it will be a bit more lecture style. I'll see whether I want to set up feedback fruits for that or not, but I think it's only a couple of questions that I would ask you anyway, so we'll see how we can make that work. All right. I think there haven't been any questions in chat, so I assume then that there aren't any. So, there we go. Daniel, can you just use the standard hash function in Python when nothing is said about creating your own? Yeah, for sure. So the hash function in Python is pretty much better than anything than anything that I can probably come up with. So when I don't mention anything, by all means, just use the regular hash function from Python. You will find, so we're going to do one exercise today. Let me just double check to see if I'm not saying nonsense. Yes, so when we ask you to implement something, for example, today we're going to take a look at a hash table exercise, then we will provide the hash function that you need to use, just so we know that in our spec test, right, you're using the one that we expect. And therefore, things become a little bit more deterministic. But in general, if I don't mention anything, yeah, please just use the Python hash function. All right. Then let's try to get started. So we'll get started today with two paper-based exercises, just because I have the tablet set up now, and it's easier for me to start with those. So for the first one, we have a hash map that starts of size 2, and well, it grows according to the rules we saw yesterday, right? So it grows every time it is at least half full. We use the separate chaining model for dealing with hash conflicts. We have a hash function that's 3 times k, modulo the map size, and I'd like you please to add all of these keys to that map. I'm going to give you a couple of minutes to work on it. Now, of course, we don't have the cups, so perhaps you can just say, I don't know, I'm done in chat or something like that. We'll see if that works. If that becomes too messy, then we'll stop doing that. But we can try, right? So a couple of minutes to work on this. Try and let me know via chat when you're done, and I'll see you in a bit. All right, I'm going to give you about 1 more minute to work on this. Again, please let me know if you think you're done. All right, let's see if we can figure this out. I realize not all of you are done yet, maybe, but let's give it a go regardless. Yeah, let's try it. So, what can we do? Well, let me first of all do this so that you can now see our improvised blackboard again. So what we could do is we could simply start adding them, right? So f of 1 is 3 times 1, mod 2 is 1. So for starters, we have our map of size 2. We put our 1 in the right place. Now we are half full, so we make the thing twice as big. We have indices 1, 2, and 3. We need to rehash this. So f of 1 is now 3 times 1 modulo 4 is 3. So the 1 goes here. And now we can add the next one, f of 8. That's 3 times 8 modulo 4. That's 24 modulo 4, that's 0. So 8 goes here. Now we are half full, so we need to double in size. We have indices 0 through 7. We need to rehash these. So f of 1 is now 3 modulo 8, that's still 3. And f of 8 is 24 modulo 8, that's still 0. And we can add the next one, 2, that's 6 modulo 8, that's 6. We can add it, and so on and so forth. Right, we could continue doing this. We can safely add one more, and then we need to double, rehash everything. But that's quite a lot of work. What we could also do is we could also simply, well, I say simply, I should say simply, right, between the quotes. What we could also do is first take a look, what is the size that our map is going to end up with? Because as soon as it becomes that size, we're going to rehash everything anyway. So why not skip all of this stuff in between and immediately take a look at that map size, hash everything for that map size, and put it in that map. So let me open a second page here, and let us try that instead. So how many elements are we going to add? Well, let's simply count them. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13 elements. Meaning the final size of our map, it's going to be quite massive. It's not going to be 8, because that would be too small. It's not going to be 16, because we're using more than half of that. So the final size is going to be 32. So bear with me. $18, $19, $20. $29, $30, all the way up to $32. Let's draw all of these cells. And now all we need to do is put each of them in the right box. And that's going to be a challenge because we're using separate shading. So if I need to make a linked list here, I'll have to see how I run into space issues, but we'll figure that out as we go. So let's start with f of 1. It's 3 modulo 32. That's 3. So 1 goes here. F of 8 is 24 modulo 32. That's 24. So it goes here. F of 2 is 6. I'm just going to skip the writing down the whole modulo part. So 2 goes here. F of 37, that's 74, that's 81, that's 111. Modulo 32 is 15. Did I get that right? If not, please correct me. If so, please tell me it was correct. 37. 3 times 3 is 9, so 3 goes here. 413872, my old student number. Yeah, I have no idea. I'm gonna leave that for one to you to calculate for me. So please let me know where I should put this. Good to hear 15's right, all right. 19 times 3 is 38, 57. 57 modulo 32 is 25. So 19 goes here. 27, 54, 81. 81 modulo 32 is 17. 17, I think. So it should go here. You can also check that one for me. This is 4 apparently. Thank you Sisquakes and Jochem for calculating it for me. So we'll put it here. 4, that's just 12. 17 times 3 is 51. Modulo 32 is 19. 9 becomes 27. And finally 89, 240 plus 27 is 267. 267 modulo for, this is not going to work. Let's try it here. 267 modulo 32. We can get 160 out. We can get another 96 out. Is it 11? Sorry, not 267 of course, but 89, the value we started with. F89 is 11, good. And is it also the case that F27 is 17? That's the last one I wasn't entirely sure of. Yes, it seems to be. All right, Sysquake Skills and On, thank you for helping me check this. So, like I said, right, we can go two ways about this. Either we can do exactly what Python would do, start with our list of size 2, add an element in, okay, now we're too small, resize, rehash, okay, now we can add one more element, now we're too small, resize, rehash. But that's a lot of work. The better thing to do, I would argue, is just to say, okay, well, what's the final size going to be? Figure that out, and then throw it all in there. Woof, you have a very good question. With separate chaining, you can't derive the final size like this, right? You only know if the map ever gets half full by doing it step by step, because there's no limit to how many values can fit in one spot in the map. So this is a very important distinction. The number of items in the maps determines when we get to resize. So not the number of filled spots, let's say, but instead the number of items in these lists, if that makes sense. Right, so let me draw a quick example. Let me do this instead. So consider this map and 5. This map, both are equally big. Right? Both contain 2 elements. So it doesn't matter whether they are in lists or whether they are in these cells. Both of them now have 2 spots filled, and so one more would cause both to trigger a resize. Does that make sense, Woofus? All right, good. 2 other quick questions came in. First of all, from Si Jing Chen, isn't the current map too large? I think you're absolutely right. Let me fix that. This one indeed should not exist, right? When we have a map of size 32, the last index is indeed 31. Yes, thank you for correcting me on it. Jochem, is it also possible for linear probing? Yeah, for sure. It works exactly the same way. So we can first determine the final size and then put all of them in there. The only thing with linear probing is that technically ordering matters a little bit more. Let me see how I can answer or how I can describe this. Because technically when we resize, we would go through the keys in order in the hash map instead of order of insertion. And for linear probing, of course, the order can determine which one is put in the right spot and which one is put a little bit later. So for linear probing, perhaps for the ordering, there would be more problems. So long as you have no conflicts, like we had over here, it's all going to be fine. But if you have conflicts, then the question is which one is going to be inserted first. And that depends on the order they were in the previous step. So for the previous size. Si Jing, did I answer your question? And Jochem, did I answer your question? While you let me know, I'm going to look at the question of Daniel. The lecture part of this tutorial, is it equal to the second lecture of last year on Glaciorama? Yes, though probably only the first half, right? Because I can't do 90 minutes of lectures in 45 minutes. We'll just have to see how far we can get. Yeah, if you would do it the other way with resizing after every step, you would again rehash just as with separate chaining. The only thing is, right, so imagine, I'm going to give you a very small example here. Imagine that we have as our hash function this thing, right, just k plus 1. And now I have the keys 0 and 1. Let me see if I can make this work. So 0 goes here. Now we resize. 0 still goes here. Yeah, I can make this work by making this not 1 but 3. Sorry for this. I need to, yeah. And now have whatever next, right? So this. What would happen here? 0, 1, 2, 3, 4, 5, 6, 7. Yeah, there we go. Is that when we transform when we do this transformation, we're first going to rehash the 3 and then we're going to rehash the 0, even though 0 was inserted before 3. Because in this rehashing, we're just going to do it in sequence of the elements in the map. Does that make sense? I need to hide my tablet for a second because it's going to show another ad again. Good, that makes sense. All right. I have one more quick question for you, and then we'll do 1 or 2 implementation assignments. Daniel, I'll answer your question in a moment when we take a look at one such question. So you asked what type of questions can we expect at the implementation exam about this part. We'll take a look at one old exam question very soon. First, let's take a look at an old exam question from a written exam. So it should be on your screen. So consider a hash map that uses a variation of separate chaining called alivio chaining. You can Google this, but well, you won't find anything because I just made it up. This version uses AVL trees to store the key value pairs instead of in the different buckets. So that's instead of the linked lists. Does this change the runtime of the put and remove operations of the map? If so, explain how. If not, explain why not. I know the slide's not centered, but there's nothing else that you're missing out on here. There we go. It was not centered so that I could have the blackboard. So again, I'll give you 1 or 2 minutes to think about this. Please wait with answering so that everybody gets 1 or 2 minutes to think about this, and then I'll ask you for some input via chat. See you in 1 or 2 minutes. All right, so let's hear it. Does this change the runtime, and if so, why and how? It changes the runtime because retrieving the index at which we access the data still take constant time. Agreed. When removing data from the tree at an index, it takes log n's time instead of n. Exactly. Yeah. So it's a bit of a tricky question, right? So you're all very right. So if we use one of these AVL trees, they had a very nice property. So Skills, Jochem, Daniel, and Vamossosum, if I pronounce it right in any way, shape, or form, all seem to be pointing towards the same thing. These AVL trees had a nice property in that we can easily find the right place to insert something. So that's putting. And we can easily find something to retrieve. And removal could also be done in log n time, right? We don't need to go through the entire list, but we know the right place to find. We could remove it and then do some bubbling to fix the AVL properties. So does that change the runtime? Well, you might now say, okay, so the worst case instead of theta n is theta log n. And you would be right. The expected runtime, however, of theta 1, I would argue, doesn't change. Because if we have our proper hash function, then the keys would be nicely uniformly distributed, and therefore there would be all trees of size 1. And AVL trees of size 1 are just a single root. Removing them or creating them takes constant time. So expected case, nothing changes, but worst case becomes a little bit better. Now if worst case becomes a bit better, why don't we just do this? Why don't we just always use AVL trees? Seems to make more sense to do so if, I don't know, becomes better. Any ideas? Daniel's pointing out space complexity. More complex to program. Horrible space maybe from Jochem, yeah. So space complexity, I'd say, doesn't really matter. At least the complexity doesn't. Both cases we need to store all the elements. It's just that in our linked list we only have a pointer forwards and backwards. And with our AVL tree we have a bit more logic with pointing to 2 children. But yeah, I'd argue that's the same amount of pointers even. So in terms of space complexity, not really a difference. In terms of absolute space used, maybe a little bit more, yeah. The main thing is what Skills is pointing out here. More complex to program. Yeah, I mean, AVL trees are a way more complex beast. That being said, many people have written perfectly fine implementations of AVL trees, but there's really no need, right? Because in the expected case, the AVL trees and the lists are going to be very, very small. And if the lists are very, very small anyway, then any benefit that we get is going to be lost because the size is so small. If these lists could contain hundreds of elements, then sure, that would be nice to use AVL trees instead of lists. But if these contain hundreds of elements, something went wrong, right? We're using a horrible hash function because keys are not uniformly distributed. How would you even say one thing is less than the other? Yeah, so that's very difficult to do when we don't talk about space complexity. What I'm trying to do in my head is visualize how would I implement this and what kind of fields do I need, right? So in a linked list, we saw that you need the head, you need, and for every node, you need a next and a previous pointer, and you also need a tail. For a tree, we need a root and we need pointers to our children, and it might be nice to have a pointer to our parent. And that's why I think that might use a little bit more space, but it's very hard to make that comparison. And in terms of space complexity, both require linear space in the number of values. So in terms of space complexity, there's no difference. Does that make sense, Om? There was one other question from Alfie. Why did the Hashmap resize to 32? So we had 13 values that we needed to input. 13 wouldn't fit in a map of size 16 because more than half is used, which is not allowed. So the next one after 16 is 32, right? We double every time. You meant in the AVL tree? Ah, I see. So in the AVL tree, we require some sort of comparison. So agreed. We would have to have some way of comparing keys. Now, if they are integers, that's fine. If they're strings, we could maybe use alphabetical order. So for most things, we can come up with something. But I agree, it's an extra requirement we put on our keys that isn't required when we just use lists. Yeah, it's a very good point. Okay. I have one implementation assignment that I'd like to do with you. So let me switch this over to WebLab, which I prepared over here. Let's see. And let me hide this. That's not what I meant to do. This is what I meant to do. Okay, so in WebLab, what we're going to do is the second exercise that is there. This is one of these old exam questions that Daniel was asking about before. So in this one, we need to implement separate chaining. So we have a hash table set up with a capacity and a table. Is the font size okay, or should I zoom in? Please zoom in. All right, can do. Let's see. Something like this, maybe. All right, good. So we have a hash table class. It has a capacity, and it has one of these lists of lists, right? We're going to use separate chaining. We already have an initializer, which just creates empty lists in all of these cells for us. And all we need to do is implement the get method. So given a key, we need to return the value for the key if one exists. If it doesn't exist, we need to return none. Again, I'm going to give you a couple of minutes to work on this, and then we'll take a look at the solution together. If you're done, let me know via chat. I'll put a timer on screen again, and I'll see you in a bit. All right, a couple of people seem to have gotten this to work already. Let's see if we can make it work together. So let's give this a go. 2 minutes left before it's break time. We can do this. All right. So, what do we need to do? We need to take the input key and return the value if the key value exists, and otherwise return none. All right. Well, let's start by checking if. Let's start by computing the hash. We'll call it h, and we'll hash our key. Now, and this is what I mentioned before, right? This is where we need to use the hash function given, just so that we make sure our tests can, let's say, use a predictable hash. So let's hash it first, and then let's try and look for the right place. So we called these things buckets before, so I'll stick with that naming. We want to get the bucket at place H. Now, what's that going to contain? It's going to contain a bunch of entries. So what is an entry? An entry is something that has a key and a value. Okay. Well, let's just do it like this. For entry in bucket, if the key of that thing is the key we're looking for, then great, we found it. Otherwise, if I've gone through all of this, well, then I'm not going to be able to find it. I think this should be all, but let's find out what the tests think. So your test passes. The spec tests, yeah, they pass too. So compute the hash of the key you're looking for, get the right bucket, go through all of them. If you find an entry with the right key, return its value, and otherwise return none. Daniel's asking, could we not just leave this out? We can. We are abusing something from Python then, namely that not returning anything is the same as returning none. When I say it out loud, it sort of makes sense, right? Not returning anything is the same as returning nothing. I suppose that makes sense. But I always like to be explicit. So I would keep it in. But you're right, without line 25 it should still work. Skills is asking me about line 21. So what we do, right, the hash of the key determines which place in the array I need to look at. And now this is separate chaining. So at that place, we're going to find a list. And that list I am now calling bucket. So I could also just say this instead and leave out this line, if that makes more sense to you, Skills. Right? All I want to do is I go to the right place, there I find the list, and I need to go through this whole list. Well, you're letting me know, Skills, if that clarifies it or not. How are we sure that H is even in there? Okay, good point. So we rely on this hash function. And fortunately, this hash function says that we modulo by the capacity of our list, meaning we must get a value between 0 and the length of the list minus 1. So it must be, H must be in there. Let me quickly knock out 2 questions of Jochem and Gideon. So Jochem, would you lose points if you wouldn't add this line? No, you wouldn't, because like I said, the Python default is to also return nothing. So it would still be completely correct. So it would be fine if you leave that out. Gideon, do we have to assume that if it's not mentioned, there's no linear probing? Well, we mentioned explicitly here that we're using separate chaining, and these are really one or the other. So perhaps you could combine them, but I'm trying to think how that would work, and I don't really see it working. So because we're using separate chaining, we are not using linear probing. Right, and with linear probing, we also wouldn't have a list of lists, but we would just have a list of entries. even without this, right? So our table would also look like this. I see I answered Skill's question. Did I also answer yours, Jochem and Gideon? Yes for Gideon. And yes for Jochem. Good. Then I'm going to send us into a break. So after the break, we'll do the first half of one of the lectures that was indeed recorded on Collegiorama last year. We're going to be talking about graphs. I'll see you about 15 minutes from now. If you have any questions in the meantime, feel free to just ask them. I'll stick around in chat for a bit after getting a fresh cup of water. See you in a bit. All right, so I was almost going to say, well, everyone is finding their seat again, but hopefully that won't be necessary. So welcome back. Just after the break means, of course, that it's time for today's intermezzo. Now, before we begin, thanks again for sticking around. I still realize Twitch is not ideal, but we're making do, and thank you very much for your cooperation on that. I think the interaction we're having through Twitch chat is actually sort of workable. Here's hoping that this afternoon with 200 computer scientists I can say the same, but we'll find out. So, today's intermezzo, let's talk a little bit about family trees. Now, I'm sure you've seen these nice diagrams before, right? You start maybe with your grandparents, then you have your parents, and then you can have you, right? But in my case, well, I have a sister too. How does this work? How is this a tree? I mean, already it's a bit weird because in the models of trees that we've been studying, you have one parent, but in a family tree, most people have two. So, okay, maybe we could just read it the other way around, right? So we have arrows. We have only one arrow going out, but that doesn't work either because, well, my mom, she has two kids. So this nomer of a family tree is one of the things that can really frustrate me sometimes, right? This thing isn't a tree. In fact, when you add in the real picture here and you include my half-brother and half-sister, this thing doesn't look like a tree at all anymore. So, although many people call this thing a tree, what we should actually be calling them is family directed acyclic graphs. You'll know in a moment what that means exactly, because we're going to be talking about these things, graphs specifically, but hopefully we also get to the directed and acyclic parts. Directed, meaning that every edge has a direction. Acyclic, because, well, unless some really weird stuff is going to happen, it's very much impossible for me to be my own grandparent or something like this. So, directed, acyclic, and definitely a graph, not a tree. So, next time someone asks you to make a family tree, how about you say, sorry, can't do that, there's no such thing. If you want, I can make you a family DAG instead. See whether that works. So far from my ranting about how these family trees should definitely not be called family trees, let's talk a little bit about graphs. So let me go all the way back here. Let me give you an introduction to graphs. So what we're going to do, I'm going to introduce the topic of graphs today, and on Thursday during our tutorial, we're going to take a look at some first graph algorithms. Things we can do using these graphs. So, what have we seen already? Well, we've talked about lists, tags, queues, trees, maps, the master method, tree algorithms, a whole bunch of stuff. Today I'm going to give you an introduction to graphs. I'm not sure if we get to the storing part, and the traversing will definitely save for Thursday. But at least the introduction I'll cover today. And next week will be all about graph algorithms as well. Shortest path, topological orderings, all kinds of fun stuff. And we'll leave P versus NP for the final week. Yeah, so this is a bit weird, but this is pretty much your last week that you can register for the final exam, assuming that it's going to take place 3 weeks from now. I don't know yet, but well, rather safe than sorry, doesn't hurt to register. So make sure that you do so in Osiris if you haven't already. Now then, let's talk about graphs. And before we do, I should talk a little bit about trees, because graphs are going to be an extension of the idea of trees. So remember that in trees we had a root with children that we called leaves, and if they were at the same level they're called siblings. We had descendants and ancestors, all of these great terms. Well, the main thing that we're going to change for a graph is that instead of only having one parent, you can have, let's say, multiple edges going up. to generalize that even more, edges can go anywhere. So this parent-child relationship is going to be replaced by just two nodes having an edge between them. Now, why is that useful? Well, let's take this as an example. Perhaps currently not the main thing on your mind, right? Traveling by public transport, but definitely something people normally do a lot every day. Now, what we're going to do is over the next 2 or 3 weeks, we're going to solve a lot of problems that the NS is facing, but again, perhaps not currently. And we're going to take a look at some questions that the NS might be asking. So the NS has a large network of trains, of course, in this country. And one of the things you might ask is, okay, if I get on a train in Delft, where can I go? Right? What other cities in the Netherlands or even outside of that can I reach solely by traveling by train? It's okay if I have to transfer train, but I only want to travel by train. Where can I go? You might then ask, okay, but what's the quickest way to get there? So when I was a student, I still lived in Haarlem. Every day I travel from Haarlem to Delft and back, and I would often ask this question, right? How do I get home the quickest? Perhaps you might be asking, okay, I have a new station. How could I connect it to my network? So what new lines should I draw? What new rails should I build to connect new stations? And finally, well, now that you have a bit of time, although I don't recommend doing this now, but you might want to take a tour through the country. Visit all of the cities in the Netherlands by train. Question is, how could you do that the quickest? Now, these are all questions that we can ask about the NS and that we can ask about graphs. And they're all problems we're going to be dealing with over the next 2 weeks. So the first one, we can do so by using traversals, which we'll talk about not today, but on Thursday. Shortest path, Dijkstra indeed, Gideon. We'll discuss that next week. Shortest path for the best way to connect new stations we can do using minimum spanning trees, which we'll talk about next week. And quickly touring the country, yeah, that's the traveling salesman problem. And we have no solution to that. But perhaps if you find one, that would get you a very large prize. So if you will have some idea of how we could solve a problem like that, 2 weeks from now we'll discuss it more formally. Get ready to present that solution to me. There's $1 million in it for you. So all kinds of fun questions that we can ask about the NS, that we can ask about graphs. But in order to ask them, let's first formalize this notion of a graph a little bit. So very informally, a graph is just a bunch of lines and circles. Here's an example. Now, we call these things special names. These circles, we call them vertices or nodes. And you'll find that I often use both in the same sentence. These really are just synonyms. A vertex is a node and a node is a vertex. Use whichever name you like. Then we have these lines. We call them edges or connections. Connections is not a name I often use. It's usually edge for me. But I'd understand what you mean when you write connection. Right, so vertices for the circles, edges for the lines. And then the graph that we have here is both undirected and unweighted. So what does that mean? Well, undirected because the edges have no direction. If we do give them a direction, we draw this as arrows and then we call it a directed graph. And it was unweighted because the edges did not have weight, but if we add weight to the edges, then we call it a weighted graph. So here we've given all of these edges a certain weight. They could, for instance, represent travel times between different cities, right? So the vertices could represent cities, and the edges could represent trains going between them, and the numbers indicate the time spent going from one city to another. Questions about the notation so far? So vertices, edges, directed, undirected, weighted, unweighted. don't think so. So let's move on to a couple more notation things. Yeah, so Jochem, if there are no arrows, so if we have something like this, then indeed the graph is undirected. So you can go from D to F in this picture, as well as from F to D directly, whereas in our directed version, we can go directly from D to F, but not from F to D. Yes, good question. Okay. Then let's make this more formal. So you're mathematicians, you might appreciate a more formal setting. Computer scientists tend to dislike this one. They prefer the pictures. But let's see how this goes for you. So if we have a graph, it has a set of vertices and a set of edges. We denote these as V and E. E is the set of edges, and every edge has two endpoints, right? Two vertices that it connects. Now we can include a weight function. If our graph is weighted, it maps every edge to a certain weight. Now this weight can, technically speaking, be any real number, but in practice we often go for positive integers. So in practice it's very, very often the case, there are exceptions, but it's very often the case that these are positive integers, especially for the use cases we will see in this course. So yeah, normally we restrict ourselves to weight functions that do that. Now then, depending on whether it's a directed graph or not, every edge E, if it's a directed graph, it's a tuple. And then we have what we call an origin and a destination, sometimes a source and a destination, but usually origin and destination. If the graph is undirected, then we don't have a tuple, but we have a set, because the ordering doesn't matter. Now, that's something I really like, and something that many textbooks do, but unfortunately also many just use a tuple notation for undirected edges and then just remark, but it's an undirected graph, so the ordering doesn't matter. I will try to be as consistent as possible and say, okay, well, undirected edge, then we have a set of tuples, or sorry, a set of vertices, and a directed edge, we have a tuple of vertices. So this is just a formalization of the notation, or the words and definitions I introduced before. Gideon, can there be a double pointed arrow in a directed graph? For sure. So then we have two directed edges, one from U to V and one from V to U. Yes. Usually we don't draw a double-headed arrow, but instead we draw two arrows with a curve to make it more clear that there's really two paths. But yeah, some people just draw one with the double-pointed, double-headed arrow. Make sense? Well, Gideon's typing whether this made sense or not. Any other questions about this formal definition? Good to hear, Gideon. Currently, I see no other questions coming in. Okay, then there's a few more properties that I want to get out of the way quickly. But before we do, we're going to draw one of these graphs. So here's a nice graph. I'd like you to draw it for me, please. I'll give you 2 minutes or so to see if you can draw it, and then we'll take a look together. Again, feel free to just let me know when you're done. That way I can stop us a little bit early if it looks like many people are done early. Okay, let me put this on. And I can set up my blackboard in the meantime. Let me unmute the mic, that tends to help. All right, let's give this a go. Let's see how we can draw that. So we have 6 vertices. I'm just gonna put them anywhere and hope for the best. What is sometimes wise is to first take a look at all the edges you have so that you can place the vertices in such a way that we can draw the edges without overlapping them too much. But I'm feeling lucky. Let's see how this goes. So what do we have? We have an undirected edge, because it's written as a set, between A and B. And thank you for that, but I don't want an ad at the moment, Visor. I should buy the upgraded version. I'll do that after the stream. There we go. Okay, so an undirected edge between A and B. Then we have an undirected edge between A and D. We have an undirected edge between C and D, between B and F, between B and E, between E and D, between E and F, between C and F. Okay, well, we're gonna have to cross here because can't make that work otherwise. And now we have some directed edges, right? As indicated by the fact that they are tuples instead of sets. So we have a directed edge from A to C, as well as from C to A. We have a directed edge from D to B. And we have a directed edge from B to C. And now we have some weights. So the weight for E to D is 8. Let me actually do this in a different color. We have from A to C, we have a weight of 2. From C to F, a weight of 5. From E to B, a weight of 2. E to B, that's this one. And C to A, a weight of 8. And all others, their weight equals 1. Right? I'm fine with you drawing it everywhere, but for readability, this is probably just as good. Does this make sense? This way of drawing a graph given its formal description? Any questions about it? Jochem, I saw you had a question, but I see also that answered it. Was that clear to you? Well, I see no questions popping up. So let me move my blackboard out of the way. Good, the question was answered. And let us switch back to the slides. So hide this, make this a little bit larger again. Okay. All right. So what else do we have for these graphs? Well, these vertices can also have some properties. So properties like what? Well, mostly some names. So two vertices are adjacent if there is an edge between them. And adjacent we can also call neighboring. So A and D are neighboring vertices, C and F are neighboring vertices. But for example, C and E, so this one and this one, are not neighboring vertices. Right? We can get from C to E, but not directly. There is not directly an edge between them. So they are not neighboring vertices. Then every set or every vertex has a set of incident edges. So that's all the edges that it is connected to. And when we have a directed graph, we have incoming edges. So in this case, for vertex C, it has two incoming edges, BC and DC. And it has one outgoing edge, CF. So for undirected graphs, we have incident edges. It's just all the edges it's connected to. For directed graphs, we can further split this into incoming, and outgoing edges. I see my camera is really struggling again. Sorry for that. I hope it will recover soon. Not yet, it seems. Give it a moment. Okay. Now, again, we can formalize that. So two vertices are adjacent or neighbors if and only if there is an edge such that that edge connects the two. The set of neighbors is all of the nodes that are a neighbor of U, which we have just defined in the previous statement. An edge is incident if in a directed setting either the edge leaves or enters the vertex. Then we have the degree of a vertex. So that's the first new thing here. The others are just formalizations of the previous slide. The degree of a vertex is the number of incident edges. Right? So for every vertex, this is at least 0 and at most, well, some number, some integer number. The degree of the vertex is the number of incident edges. And of course, for a directed graph, we can define an in degree and an out degree. In degree is all of the edges coming in, and the out degree is all of the edges going out. Or the number of edges coming in and the number of edges going out. I'm just going to continue, but again, if there are questions, please do ask them. And yeah, so since the degree of the vertex is all of its incident edges, which, like I said, for a directed graph, we can split into two parts, add them together, you must get exactly the degree of the vertex. Okay. So, with these definitions in mind, 1 minute to figure out this answer. Since this was the only question I think I was going to ask in feedback fruits, maybe this one and one more, I didn't bother setting it up for today. I'll see if I can figure out something else, but take a minute first, see if you can figure this out. All right, I tried to set up some sort of poll in Twitch, but that is not at all what I expected it would do. So yeah, we can use this, or we can just... Okay, so some people are filling it out. Why not take 20 seconds to give me an answer via this straw poll you can find in chat if you want to, and then we're going to take a look. All right, let's see. Does this do anything? So it does. So answer C is the most popular with 12 votes. Some more are still coming in. Let's figure this out. So the outs degree of D. D has 3 edges leaving it, so that's 3. Then the in degree of C. C has 2 coming in, so 3 plus 2, that's already 5. And now we have the sum of all of the vertices such that B is connected to the vertex. And then its degrees. Well, B is connected to C and E. The degree of E is 4. 3 coming in, 1 going out. So 4 plus 5 that we already had is 9. And then we need to add the degree of C, because B is also connected to C. That's 3. 9 plus 3 is 12. So answer C is indeed the right answer. Questions about that? Silence, so I guess not. Let's continue then. Now, what we have looked at so far is one way of defining a graph. There are some alternative definitions or extensions, if you will. So consider, for example, a graph that has a collection of edges rather than a set. What does that mean? Well, it means that there could be multiple edges between the same pair of nodes. We call these things multigraphs, right? So now there's 2 edges from D to F. What we can also have is we can have self loops. So we have an edge from B to B or from F to F. And we can have graphs. I was not going to mention the last extension anymore. Okay, so these are 2 possible extensions. But in our course, so far I have not come across any counterexamples to this. So we only consider simple graphs. So that's where E is a set, meaning there can only be at most one edge, at most one directed edge between the same pair of vertices. Okay, that's also not a nice way of saying it. We could go from D to F and from F to D, but we can't go from D to F twice. And we also consider no self loops. So we call these simple graphs. Okay, why is it useful to do consider variants of this? Well, so these multigraphs especially can be nice when there's multiple ways to get from one city to another, for example. Right, so we could have different edges represent different ways of getting somewhere. We would model this by having more vertices, but you could do that another way. Okay, then let's take a look at something about these edges. So we saw something about these nodes, right? They have in degrees, out degrees. Now let's take a look at a sequence of edges. And then we have a path. A path is a sequence of edges that are all connected. What does connected mean in this case? Well, it means that the endpoint of one edge is the start of the next edge. So in this case, A to B, and B is now the start for the next edge, B to C. Paths could contain the same nodes twice. So the path that I've drawn here starts at A, and it goes in a nice loop, and then back to A and then to E. That's all fine. However, in a simple path, okay, first we talk about cycles. Okay, in a simple path, we cannot have this repetition, but we'll talk about simple paths in a moment. So in a regular or in any old path, without any extra qualifiers, it's perfectly possible for a node to appear twice. A cycle is a path that starts and ends at the same vertex, as you may expect. And now there we go. So simple paths and simple cycles allow every vertex at most once, with the exception that for a cycle, the start vertex is also equal to the end vertex, right? Because we still need to have the cycle. So there's one vertex that we have twice, but all others we cannot visit more than once. Paths and cycles. Now this was the computer science explanation with a nice visual. Let's look at a bit more formal explanation. So a path we commonly call pi, because why not make this a little bit more confusing? So a path pi is either a sequence of vertices or a sequence of edges, where the sequence of vertices is more commonly used for simple graphs because the vertices indicate which edges you must use. If we denote it in such a way, then for every consecutive two vertices in the sequence, so from A, B, C, for example, there must be an edge from A to B and from B to C. If we denote it as a sequence of edges, then it is only a valid path if and only if two consecutive edges share a node. So U goes to V, and from V we depart to W. And finally, a cycle is just a path, with the exception that the last is the same as the first. For directed graphs, we can talk about directed paths and directed cycles. So far, so good. Any questions about this? Well, if there are, I'll see them pop up soon. Let me give you one more of these questions to work with. So, so we have our same graph again, right? How many vertices are part of the longest simple path in this graph? So try and find me the longest possible simple path in this graph. I'll give you a minute or so. If you want, there is a poll available in chat that you can use to give me your answer. All right. Last few answers are still flooding in. 17 so far. 5 more seconds to give me one if you have one, though I realize that with the delay, that 5 seconds should actually be a little bit more on my end. All right. 3/4 of you for answer C. Yes, could someone quickly give me the path? So what is this longest path of length 6? or, well, how many vertices are in there, right? So can you give me the path with 6 vertices? That's not the one I had in mind, so that's always interesting. Let's see. E, F, D, A, B, C. Yes, so that definitely works. The one I did have in mind is the one given by Vamos and Jochem, I think. B, C, F, D. Does that work? Yeah, A, E, right? So we can go like this. Alternatively, A, B, C, F, D, E, as pointed out by A, B, E, F. Yeah, okay, so there's plenty of options, right? Everything I've seen so far in chat, I think, works. So well done. Yeah. Plenty of options, all have indeed a length of 6. Now, fun fact, most of you were able to solve this, but this is one of those problems that for us computer scientists is still a problem that we don't know how to solve efficiently. So for, let's say, graphs a little bit larger than this, the best option we've got is to simply try all the options. And we can do that in a somewhat smart way. But this is one of the problems for which we have no polynomial time algorithm, as we call it. We only have exponential time algorithms for this. And that is something we will touch upon again in our last week when we discussed P versus NP. So perhaps somewhat easy to solve on a piece of paper if you have a relatively small graph. But for larger graphs, doing this with some code, we have no idea how to do this efficiently. If you do, well, again, let me know. We can make a lot of money together. So let's see. I think this is all I wanted to talk to you about today. Almost, okay. So 2 more definitions to go through. We say that a node is reachable from another node, if and only if there is a path from one node to another node. I'll get to your question in a second, Lot. Let me finish this up first. Then a directed path graph is strongly connected if all vertices are reachable from each other. So reachable means I can get from a node to another node. Doesn't have to be directly, could be, but it could also be indirectly, right? There's a path from U to V. And strongly connected for a whole graph means that any pair of vertices is reachable from one to another. So between any pair of vertices, there is a path between them. And finally then, we have this notion of our directed acyclic graphs, this thing of our family trees, right? Our family DAGs. So a directed acyclic graph is a directed graph without cycles. It's everything the name implies. And you should now know what that means, right? So directed edges means edges going one way but not the other. Acyclic meaning no cycles. Graph, you know what that means as well. And then the next slide should be the intermezzo. There was one more question. Well, we're going to skip that one. We might save it for Thursday's tutorial. Let me quickly answer Lotte's question. So why wasn't A, E, F, D, A, B, C a simple path? Jochem and Om are indeed pointing you to the right answer here. A is used twice in that path. And remember, for a simple path, we need to go back a couple of slides, but a simple path allows every vertex at most once. So indeed, in your path, A appears twice, and so unfortunately, it's not a simple path. Good, all right. That's all I wanted to talk to you about today. So once again, thanks for being here. I have another lecture to give an hour from now, and I quickly need to go and grab an adapter for that. So I'll stick around in chat for about 5 more minutes to see if you have any questions that I can answer. Recording will be a bit later today because, like I said, I need to run now. I'll see you back on Thursday, 8:45, for our tutorial on graphs, in which we look at graph traversals. Thanks again for being here today. Thanks for making this work with me, and I'll see you on Thursday.